In this video, we consider model formulation and misspecification testing. So in practice, when we do econometric modeling, we don't know what the correct model is. So it means that in reality, we do some kind of searching for a preferred model. Say, what kind of regressor should we have in a linear regression model? What should the lag length be if we are dealing with dynamic models? And what kind of model should we actually have? Say, should it allow for time-varying heteroscedasticity or something else? In this course, we will focus on the principle of general to specific when we find the preferred model. So the main idea is that we start out with quite general model and then try to reduce it. And at the end of the day, we would like to have a well-specified model. The main idea is that if we include some irrelevant regressors in a, say, linear regression model, then their coefficient should be equal to 0, but a well-specified model should be able to capture this in the sense that if we estimate some parameter beta that has correct value equal to 0, then our estimator should simply just converge to this value. So it means that it might not be that costly to actually start out with a quite general model. An alternative would be to start out with a very specific model, say a small model, and then try to include some additional variables, say, so to make it more general. But the problem is that if this specific model or small model is misspecified initially, then the estimators of the model parameters may not be consistent. So this is well known if you have, say, a dynamic linear regression model where you have omitted some lags, implying that the error term is autocorrelated. In that sense, the least squares estimator will not be consistent for the regression coefficients. So that's a fairly dangerous approach to apply in time series analysis. One should note that for some models it may not be a good idea to start out with a very general model. So for instance, in the case of ARMA models, we may have so-called canceling roots. We will get back to that later on, but for this kind of models here, it might be a good idea to start out with a fairly general model, but not too large. Note that in practice we can never prove that the model is entirely correctly specified, but the main idea is that we want to build some models that can capture the main features of the data, or at least the features that we are interested in modeling. What we'll do in practice is to carry out so-called misspecification tests. So if, for instance, if we are considering a model that should have an error term that is not autocorrelated, we can actually test if this error term is autocorrelated. And likewise, we can test if the error term is normally distributed, and so on. So in the following slides, I will consider the most important misspecification tests within time series analysis. We will consider two different kinds of statistical models when presenting the misspecification tests. First, we can consider the well-known linear regression models for time series. We can estimate the model parameters by maximum likelihood estimation. And of course, if the error term is normally distributed, then the maximum likelihood estimator corresponds to the least squares estimator. Another class of models that are relevant is the class of ARMA models, and we can estimate this by maximum likelihood estimation. In this setting, we will assume that epsilon t has some distribution that might be unknown, and for a particular test, we will assume that the error term is Gaussian. In practice, we of course do not observe the error term, but based on the estimated parameters, we can compute the estimated residual. So if we estimate, say, beta, we have the beta hat, and then we can solve for epsilon t and denote this epsilon t hat. We denote this first class of models here with 1 star and the second class with 2 stars. It shows up that not all of the tests are relevant or valid for all of the models, but that will be emphasized in these slides here. So for the first class of models, the linear regression models, we can test if the error term is autocorrelated. So what we can do is that we can estimate that the model and compute the estimated residuals. Then we can consider a so-called auxiliary regression, so where we regress the residual on the regressor variables from the linear regression model, and then some lagged values of the estimated residuals. The null hypothesis for no autocorrelation is that all of these gammas here from gamma 1 up to gamma h are all equal to 0, and the alternative is that at least one of the gammas is different from 0. We can test this hypothesis by a so-called Royce-Godfrey Lagrange multiplier test. What we do is that we carry out this regression, save the r squared, and then we can compute a test statistic simply given by t times r squared, where t is the number of observations in our data. Under the null hypothesis, it holds that this test statistic here is chi-squared distributed with h degrees of freedom, so the number of gamma parameters in the auxiliary regression. And this h here corresponds to the order of the autocorrelation. For both of the models, the linear regression model and the ARMA type models, we can, as an alternative to the Lagrange multiplier test, carry out a so-called portmanteau test. The main idea is that we have the estimated residuals, and then we can compute their empirical autocorrelation function. We can then compute a test statistic based on these empirical autocorrelations, and this statistic here will, under the null hypothesis, be chi-squared distributed with h minus p degrees of freedom. So here h is the order of the autocorrelation, and p is the number of the autoregressive and moving average terms in the original model. Clearly this test here only holds if h is greater than p. We may also test if the errors are heteroscedastic, and we can do this by considering a test for no heteroscedasticity. We can again consider an auxiliary regression where we regress the squared estimated residuals on all of the regressor variables and all the squared regressor variables. The null hypothesis is that the error terms are homoscedastic or not heteroscedastic, meaning that we should have that all of these phi parameters and the delta parameters here are jointly equal to 0. And the alternative is that at least one of these parameters here are different from 0, meaning that the variance of the error term depends on at least one of these regressor variables. Based on this auxiliary regression, we can compute the r squared, and we have the number of observations, so we have this Lagrange multiplier statistic t times r squared, and this will be asymptotically chi-squared distributed with 2 times k degrees of freedom under the null hypothesis. Here k is the number of regressor variables from the original linear regression model. One can also extend this test to allow for cross terms in the auxiliary regression. Another type of heteroscedasticity in a model is the so-called autoregressive conditional heteroscedasticity, known as so-called arch effects. If the error term has arch effects, then the conditional variance of the error term depends on the lagged values of the squared error terms and is hence time varying. Later on in this course, we will consider the so-called class of arch models and how these can be used for modeling financial time series. In order to test for arch effects, we can consider the following auxiliary regression. We consider the squared estimated errors, and we regress it on a constant and some lag values of the squared estimated errors. up to order h. The null hypothesis of no arch effects is equivalent to testing for gamma 1 up to gamma h being equal to 0, and under the alternative, at least one of these parameters here should be different from 0. Again, we can consider a Lagrange multiplier statistic, and based on the r squared from this auxiliary regression, and under the null hypothesis, we have that the test statistic is chi-squared distributed with h degrees of freedom. Note that this test here holds for both the linear regression models and the ARMA class of models. We can also consider a test for correct functional form of the model, the so-called reset test. Again, we consider an auxiliary regression where we regress epsilon t hat on the regressor variables and on the squared predicted values from the regression model. So yt hat here is xt prime beta hat, where beta hat is the estimator of the regression coefficients. The null hypothesis of correct functional form is that this gamma here is equal to 0. Under the alternative that gamma is different from 0, we have that some term containing a squared regressor has been omitted from the regression model. We can consider a Lagrange multiplier test, and the test statistic is chi-squared distributed with 1 degrees of freedom. Lastly, we may consider a test for normality of the error term. This can be done quite informally by simply plotting the estimated errors or the residuals and simply consider whether this appears to be normally distributed. If we have some extreme values of the residuals, this suggests that the errors may not be normally distributed, and it could indicate that there's been some extraordinary event at a given point in time. Note in general that the misspecification tests are fairly sensitive to outliers or these extreme values of the residuals. In order to deal with these extraordinary events, we may include a dummy variable at these points in time, so they kind of explain this extraordinary event. This does not mean that we should always just include dummy variables in a regression model to remove outliers. Of course, these outliers might be important for our analysis, so including these dummy variables essentially means that we don't expect our model to be able to deal with these extraordinary events. But of course, it could be that these extraordinary events are quite important for our analysis, and then we actually may want to consider some alternative model that should be able to capture these events directly, not with a dummy variable. Of course, in practice, one can explain everything in a data set by simply including a dummy at each point in time. This model will kind of explain everything, but of course it might not be useful at all for doing any hypothesis testing or for any kind of forecasting. We can make a formal test for normality of the error term. We may define the so-called skewness and kurtosis of the error terms, where the skewness is the third moment of the error term. Note that I have here standardized by the standard deviation of the error term, and the kurtosis is the fourth moment of the standardized error term. If the error term is normally distributed with mean 0 and at variance sigma squared, then it should hold that S is equal to 0, meaning that the error term should have a symmetric distribution, which is the case for the normal distribution, and it should have so-called no excess kurtosis. So K should be equal to 3, such that K minus 3 should be equal to 0. As I mentioned, we don't know in practice what the error term is, so we can consider the residuals or the estimated error terms. We can compute the sample counterparts to S and K simply by taking the sample third moments of the standardized residual and the sample fourth moment of the standardized residuals. One can show that under normality, these two estimators are asymptotically normally distributed with some given variances. Doing a bit of math, one can consider the squared versions of these and then standardized by their variances. So this gives us zeta s and zeta k, and these two quantities here are asymptotically chi-squared distributed with 1 degree of freedom. Then again, under normality, one can show that these two statistics are asymptotically independent. So it means that if we consider the joint hypothesis of S being equal to 0 and K being equal to 3, then the sum of these two statistics here should be chi-squared distributed with 2 degrees of freedom. So this sum of the statistics here is the test statistic that is relevant. Note that all of these misspecification tests are standard estimation output in Oxmetrics. Let us consider a simple example for the real house prices in Denmark. So this dataset here contains the house prices and the consumer price index for the Danish economy from the beginning of the 1970s until 2004. So this is quarterly data. Based on these two series, we may construct an index for the real house prices given by the log of the house prices divided by the consumer price index. We can consider this series here and its first difference. We will focus on the change in the real house prices, so this DP series. Let us consider an AR3 model for this series here. Here we get the estimation output. We can see that the error term does not appear to be autocorrelated. So we have this Lagrange multiplier test for no autocorrelation of order 5, and we get a p-value of around 13%. There appears to be some arch effects. We reject the null of no arch, but we also reject the null of normality, and we reject the test for no heteroscedasticity. And note here that this hetero X test, this is the test that also includes the cross products of the regressive variables. This is also rejected, and likewise we reject the null of correct functional form. Note that importantly, the test for no autocorrelation is not rejected, meaning that the OLS estimator here should be consistent for the regression coefficients. In order to deal with the heteroscedasticity, we may, instead of the usual standard errors, report heteroscedasticity robust standard errors. If we just ignore the reset test and simply conclude that the error term appears to be not autocorrelated but heteroscedastic, we may rely on these robust standard errors. We can see based on these robust standard errors, we have a t statistic for the lag order of 3 that is around 0.1. So it suggests that we may omit this term from the regression model. We get this AR2 model instead. Again, relying on the robust standard errors, we have that the t statistic for the autoregressive coefficient of order 2 is about 0.3, again suggesting that we may omit this second lag in the regression model. Then we are left with an AR1 model, and this term here appears to be significant. We have a t statistic of 5.4 approximately. We have that this model here is well specified in the sense that the error term appears to be not autocorrelated, but there is still some heteroscedasticity in the error terms, and indeed the error term is not normally distributed. As I mentioned, these misspecification tests are quite sensitive to outliers in the residual, so we may try to see if there are some outliers in the model, and then we may get rid of these outliers by including some time dummies. So we can try to plot the residuals. Here we can see some fairly extreme observations. Here we have one at the second quarter of 1983 and one in the first quarter of 1987. Note that the residuals here are scaled by the estimated standard deviation of the residuals. So these are epsilon t hat divided by sigma hat. These are more than 3 standard deviations from 0. If the standardized errors were actually standard normal distributed, the probability of exceeding 3 standard deviations is less than 1%. It's around 0.2%. So it's fairly unlikely to have such extreme observations if the errors were actually normally distributed. Consider the most extreme residual, so we can simply print the residuals that exceed, say, 3 standard errors. And these are exactly the 2 quarters that I mentioned, so the second quarter of 1983 and the first quarter of 1987. We can try to get a better specified model by simply including a time dummy for these 2 dates. I'll do that here by and likewise we can consider a dummy for the first quarter of 1987. So we have 2 additional variables in the dataset, namely the 2 dummy variables, and we can include these 2 guys in the AR1 model. So we can see that the error term is still not autocorrelated, and now we do not reject the null of normality. There still seems to be some issues, at least borderline, with the heteroscedasticity. But overall, this model here is slightly better specified than the one without the dummy variables. So this table here summarizes the estimation output. Thank you for watching this video.